Okay, welcome back. You should have finished the spring energy conservation practice problem. Problem, yeah, singular. Um, so now what I'm going to do is I'm going to go through the solution to that problem, then we're going to move on to power. All right, a ball of mass 5 kilograms rolls down a hill with a height of 8 meters. It hits a spring with a spring constant K equals 25 newtons per meter. How far will the spring compress? So this is an example of what we can do with springs. So rolling down a hill, we've got some movement, we've got maybe some gravitational potential energy in there. We might have some spring potential energy. Let's analyze and find out. So if we start with our energy bar chart, we have KEI, UI, work, KEF, UF. Okay. So kinetic energy initial is going to be a 0. Potential energy initial, yes, absolutely. What kind? UG. Gravitational. Work is going to be a 0. Kinetic energy final is also going to be a 0 because when the spring is all the way compressed, the ball will stop moving. Potential energy final, well, we know we have to have some. What kind is it? UK. Spring potential energy. Come on. Okay. So what are we going to do? Well, we need to calculate how much gravitational potential energy there is. MGH. So UG is 5 times 9.8. What is going on here? Times the height of 8 meters, giving us a grand total of, calculator, 392 joules. We know that that has to equal the spring potential energy. So we know that 392 equals 1/2 kx squared. So 392 equals 1/2 k is 25. And we have x squared. So if we divide by 1/2 times 25, okay, we end up with 31.36 equals x squared, square root both sides, and we get that it compresses 5.6 meters. Okay, awesome. All right. So we are going to look at a Mythbusters video. Hooray! So what you're going to do is you're going to exit out of this video and find the video titled Reverse Engineering. We're going to pay attention to the death by surfboard particular portion, the myth of that video. And I need you to do some calculations here. So a surfboard weighs about 3 kilograms, and the surfboard needs to reach 17.8 meters per second to meet the myth conditions. If the team stretch the elastic band 1.5 meters to get the surfboard to hit 17.8 meters per second, what is the spring constant of the elastic band that they use to fling the surfboard in the myth? So I would write those numbers down. Go ahead and find that video in my purchases on YouTube. Yes, I do spend money on you wonderful little bundles of joy. So go ahead and put that, I guess, on the back of the spring conservation of energy practice problem and turn that in just basically in that packet. So do the calculation, watch the video, enjoy it, and come back to this video when you are done. Okay, I'm going to assume that you have watched the video, done the calculation, and let's move on. So the next concept that we're going to deal with is called power. Power is, again, a very specific definition for us physicsy people. Power to a physicist is the amount of energy transferred divided by the time that it took to transfer that energy. So how much energy goes in or comes out of a system in a particular period of time. Finally, something that makes sense, the symbol for power is P, capital P, and the unit is watts, which is a capital W, which really is a joule per second. The formula is really either, it's what you would think it would be, and it's very simple. Right here, it's power is the change in energy over the change in time. Delta E over delta T. Pause this if you need to write this down. Otherwise, moving on. So, if a light bulb gives off 100 watts of power, how much energy does it transfer in 20 seconds? Great question. Go ahead and think to yourself, then respond. Okay, the correct answer is going to be 2,000 joules. 100 watts equals delta E over delta T, where our delta T is 20 seconds. So if you multiply by 20 on both sides, you get a change in energy of 2,000 joules. All right, if a battery drains from 500 joules of chemical potential energy to 300 joules over 4 seconds, what power is it delivering? Think to yourself, then respond. Okay, so we're going to need to actually calculate delta E in this case, and that's going to be energy final minus energy initial, which in this case is 500 minus 300, giving us 200 joules of energy change. So if power is 200 joules of energy change over 4 seconds, that gives us 50 watts. There's your answer. Okay, the question now is, how are we going to use power in conjunction with the conservation of energy concepts? So power, delta E over delta T, how much power does it take to accelerate a 2-kilogram rocket from rest to 5 meters per second over 10 seconds? So I'm going to skip the energy bar chart for this one because it's pretty straightforward. So first of all, the kinetic energy initial, since it starts at rest, is going to be 0 joules. The kinetic energy final is going to be 1/2 mv squared, which is 1/2 times 2 times 5 squared, or 25 joules. So we're going from 0 to 25, meaning delta E is 25 joules over a time of 10 seconds, giving us 2.5 watts of power. Okay. Pause if you need to absorb that. All right, next is a problem for you to try. An Olympic weightlifter lifts a 50-kilogram barbell from the ground to above their head, a height of 1.5 meters, in 0.5 seconds. What is the power exerted by the lifter? So I'd like you to pause this, go up to the big whiteboards and work this problem out with a partner or a team, and then come back to the video when you're ready to go. Okay, so here's what we need to do. We need to see, okay, we're going up. We're going against gravity, so that means we're going to gain some UG. The UG initial is going to be 0 joules because we're going to start on the ground. The UG final is going to be MGH, which is 50 kilograms times 9.8 times 1.5 meters, giving us, okay, 50 times 9.8 times 1.5 gives us a 735 joules. So our change in energy is from 0 to 735, meaning 735, not 737, 735, divided by the time of 0.5 seconds, giving us a total power of 1,470 watts of power. All right, I would now like you to complete the power worksheet. It should not take you very long. The answers are on the sheet. Okay, and that's really all I have for you. So depending on where we are in the week, you can, if you finish all of your work and turn it into the drawer, then you can watch some Mythbusters episodes. You can watch some Kurzgesagt or some CGP Grey, SciShow. Smarter Every Day is a good one. So keep it science related. And otherwise, if you need to finish any of your work over shop week, you can do so. It just needs to be done by the time I get back. So thanks very much. Enjoy your life. Be good. You're great. Bye-bye.